Hello everyone, I am Samit, a PhD fourth year student at IIT Indore. So today I'll talk about the effect of calibration error and instrumental noise on H1 map from the epoch of reionization using the largest cluster statistic. So these are my collaborators for this project. So this is the motivational slide for of this talk. So my aim is to track the history of reionizations by quantifying the morphology of the ionized region during different stages of reionizations. So these are the current and the future radiant interferometer that are used to detect the fluctuation of the 21 centimeter signal. The upcoming SK1 law will make the tomographic map of the from UR. So the construction of LSK1 law is is in progress. So it is essential we need an image analysis tool to extract from significant information from such future observations. So there is significant amount of work has been done based on percolation theory that track the history of reionization of 21 centimeter field from the simulated tomographic images. So I'll talk about the percolation process of reionization in a while. However, the observation of the recipient 21 centimeter signal is very challenging experiment. One of the major obstacle is the astrophysical foregrounds, and adding to this instrumental effect, ionospheres and other systematic, as discussed by previous speaker, that distort the target signal to a great extent. So this motivated to me that how this effect will impact on the history of reionization. So in the early stage of reionization, the small group of ionized regions are formed, and these are isolated. So these isolated ionized regions grow with time and abruptly merge together and form a singly connected largest ionized region. So this phase transition of the ionized region is known as the percolation transition. And we identify the percolation transition is happening when the largest ionized region stretches from one end to the other end of a simulated volume due to the periodic boundary conditions. To study the evolution of the largest ionized region, we use the techniques called the LCS, which is the ratio of the volume of the largest ionized region to the total volume of the ionized region. So at the onset of the percolation, the LCS value is nothing but the normalized volume of the largest ionized region, which is grow at rapid. So the previous studies by Bag et al., Pathak et al. Shown that LCS can be a good metric to study the history of reionization. Also, it can distinguish the extreme model of reionization. So to study the LCS from a simulated observations, so we develop a pipeline which is 21 centimeter E2E pipeline based on Oscar and the CASA. So this is the schematic diagram of our end-to-end pipeline look like. So this is the H1 map. We are passing through this pipeline and we are getting the observed map. So this is the observational parameter, and this is the telescope configuration of SK on low AF4 within radius 2 kilometers. So this is the visual representation of the slices that illustrated the impact of the synthesized beam of the radiant interferometric array of that is SK on low. So this is the original map, and rest of the three is the synthetic map from the simulated observations. So after run this LCS, we observe the convolutions of the synthetic beam of SK1 low with the target signal shift the apparent percolation transition toward the lower receipt or in the latest stage of deionizations. So in the histogram of the H1 field have a bimodal feature. One is peak is ionized, another peak is neutral. So for radiant interferometric array, we detect the fluctuation of the H1 signal. So the minimum value of the brightness temperature map is treated as ionized. However, in the real observations, due to the systematic effect, it shifts the pixel value randomly. So it is created challenging to distinguish the map. So here we use the triangle method to binarize this map. So after apply this triangle method, we found the obtained LCS from simulated map, which is represented by the red color, and this follow this original map. But you can see there is some little bit deviation, which is coming from the resolution of this telescope. Now to test the robustness of the LCS, we added the residual foreground, which is coming from the antenna-based calibration error. And we vary the antenna-based calibration error, and we want to figure out that, that how much the maximum tolerance level to recover the history of reionization in a robust and relatively unbiased manner. So this is the visual representation of the once a slice, the map of the residual data up now for different gain calibration error. You can see that how these unsubtracted point sources impact on the dynamic range of the images. So we found that inaccuracy of 0.05%, the post-calibration error, the obtained LCS following this observed in the LCS without any error. So this 0.05% we taken as a maximum tolerance limit for an optimistic case for LCS analysis. So, so also one important thing to note that so so if the tiny amount of calibration error is present in the data, it can affect the apparent percolation transition, which is represented by this green line. And these values should be varied depending on the statistical distribution of the bright sources, that which patch of sky you're looking for. And we also see the similar kind of effect on present in the data, present on the point sources and the diffuse foreground. And also to test the robustness of the LCS further, we added the uncorrelated Gaussian noise in the visibility domain. So this is the visual representation of map before and after adding this instrumental noise. And you can see that how this instrumental noise it introduces this small scale feature. So we see that our bimodal distributions, the feature of the bimodal distribution is lost and is shifted toward the Gaussian distribution. So when you apply this thresholding technique, so this leads to the wrong interpretation of the LCS. So to mitigate this, we applied one of the technique, which is employed the entropy-based thresholding technique to binarize this map, and we found out that at the accumulation time of 2000 observations is essential to suppress the small scale fluctuation, and you can see that at the higher network fractions greater than 0.7, the feature of LCS is lost due to the resolutions and the small scale fluctuations. And this is my summary slide. Thank you for your time.
I was just curious how you came across this LCS method. Was it empirical or is there a mathematical basis for this statistic?
Sorry, could you please? Is a mathematical basis for this, which is basically based on this Minkowski function.
If not, I think let's thank Samit again.